Welcome back to the video series entitled From the Ancient Greeks to Isaac Newton, Early Astronomers and the Birth of Science. Lecture 4, Isaac Newton. This video contains a heavier dose of mathematics compared to the first three videos in this series. I felt this approach was necessary in order to provide the audience with an appreciation of Newton's genius, and with some insight into how he arrived at his greatest discoveries. The good news is that even though Newton famously invented the calculus, audience members do not need to know calculus in order to follow along in this video. For the most part, understanding how he arrived at his three laws of motion and his universal law of gravitation requires only a familiarity with geometry, algebra, and a bit of trigonometry. Isaac Newton entered Cambridge University as a student at age 19. By age 26, he had been appointed to the prestigious position of Lucasian Chair of Mathematics at Cambridge. Around that time, according to manuscripts of his, which came to light only after his death, he proved that for a planet in a circular orbit, the gravitational force must be inversely proportional to the square of the distance from the Sun to the planet. Yet he did not publish his discovery, and he apparently told no one. 16 years later, the young astronomer, Edmund Halley, traveled from London to Cambridge to ask Newton a question that he had been discussing with two of his fellow members of the Royal Society, Christopher Wren and Robert Hooke. The question was this: what kind of curve would be described by the planets supposing the force of attraction toward the Sun to be reciprocal to the square of their distance from it? Without pausing, Newton answered, an ellipse. When Halley asked how he knew, Newton replied simply, I have calculated it. Halley was astounded. He and Wren had merely suspected that Kepler's elliptical orbits mandated an inverse square law. Hooke had boasted that he could prove the relationship mathematically, but Halley did not believe him. In fact, Hooke never produced his alleged proof, despite Wren's offer of a reward to any one of his colleagues who could solve the problem. Halley asked to see Newton's proof. Newton, who wrote a prodigious number of unpublished manuscripts, was unable to produce the document in question. However, at Halley's urging, Newton promised to reproduce his calculations and put them in writing. 11 months later, Halley received the initial product, a 9-page manuscript entitled On the Motion of Revolving Bodies. Halley was eager to make the work public, but Newton asked him to hold off. Newly inspired, Newton first wanted to complete a comprehensive analysis of the many implications of his formalized laws of motion and of gravitation. The result, published in 1687, was Newton's magnum opus, the Principia, the single most important treatise of the scientific revolution. Newton's three laws of motion and his universal law of gravitation served as the theoretical foundation for just about everything else found in the Principia, including not only his derivation of Kepler's three empirical laws, but also a variety of other phenomena, such as, for example, the variation in the magnitude of the tides from one day to another, and the precession of the Earth's axis over a cycle of 26,000 years. When we are taught about Newton's laws, we are rarely told where they come from. Did he invent them all by himself? Or did he follow the suggestions of other authors before him? Let's keep that question in mind as we begin by discussing his three laws of motion. The law of inertia states that a body moving with a constant velocity, including a velocity of 0, will continue with that same velocity unless a force acts upon it. This law follows directly from Galileo's work, as I suggested in the prior video, and it had been codified by Descartes after Galileo but before Newton with slightly different wording. Descartes' first law of nature states that each thing always perseveres in the same state in which it lies, and when once moved, always continues to move. Within the law of inertia, we already see the seeds of the second law. If a body is not moving with constant velocity, it is by definition accelerating, and a body does not accelerate unless a force acts upon it. So, what is the mathematical relationship between force and acceleration? The second law is exquisitely concise. Force equals mass times acceleration. We will see in a moment how the second law dovetails with Newton's law of gravitation and how they both rely heavily on Galileo's work. But first, let's explore law number 2 a bit more. Every force must have a cause or a source, although we may not always understand that source. In the case of a water skier, it is the motorboat that provides the force. Force is the cause of the motion, and acceleration is the result. In a sense, mass, meanwhile, is a measure of resistance to acceleration. So, for a given force, an increase in mass will result in a decrease in acceleration. Recall that Kepler proposed that all heavenly bodies possess a mutual attraction for each other. Newton not only endorsed this view, he generalized the concept and made it his third law of motion. For every force, there is an equal, opposite, and reciprocal force. That is, every force implies an interaction between two bodies. The third law applies not only to pairs of heavenly bodies, involving the sun and a planet, or a planet and a moon, but to every such interaction. It is intuitively obvious that the force generated by the motorboat pulls the water skier. It is somewhat less intuitively obvious that the mass of the water skier generates an equal, opposite, and reciprocal force that creates drag on the motorboat. Now we come to Newton's universal law of gravitation. The force due to gravity equals g, Newton's gravitational constant, times m sub 1 times m sub 2 divided by the square of the distance between the two bodies, r squared. Let's reconstruct how Newton arrived at it. On the Earth, as an example, and borrowing directly from Kepler, Newton would say that the force of gravity is proportional to the mass of the sun times the mass of the planet. More generally, the force between any two bodies is proportional to the product of their masses. And, importantly, inversely proportional to the square of the distance between them. In this version of the law, you see Newton's gravitational constant g. It's simply a constant of proportionality, which allows you to replace the proportionality symbol with an equal sign. In most discussions of gravitational force, one body is clearly more massive than the other, and so it is conventional to write the formula with a capital M representing the mass of the larger body. As Newton's law of gravitation is a universal law, you can also, of course, apply it to bodies falling toward Earth. Newton correctly deduced that for objects falling near the surface of the Earth, r is the distance from the body to the Earth's center. Now, in this famous experiment shown here associated with Galileo, the solid ball has more mass, so the gravitational force acting upon it is greater. However, because the solid ball has more mass, its resistance to acceleration is also greater by the same amount. So the two balls accelerate at the same rate. Let's derive this result explicitly by referring to Newton's second law. The force of gravity equals the mass of the ball times A sub g, where the subscript g indicates that the acceleration is due to gravity. Now, we can combine these two equations to arrive at this result. Now, dividing both sides by little m, we get A sub g equals g times capital M all divided by r squared. That is, the acceleration due to gravity depends only on the mass of the Earth and r. The mass of the ball is irrelevant. We will need this formula later. As I mentioned earlier, Newton had suspected the inverse square law was correct long before he knew of the speculations of Hooke, Wren, and Halley, and he found a proof that the law was logically consistent with Kepler's laws in the case of circular orbits. A circle is a special example of an ellipse. As we shall see, a circular orbit has specific features that greatly simplified Newton's analysis during the earliest phase of his investigations. If the inverse square law proved true for circular orbits, Newton could proceed in trying to prove it for all elliptical orbits with some confidence that he was on the right track. Here is a short summary of the logic behind Newton's proof. He took as his premises Kepler's second law and an inverse square law. He did not assume Kepler's third law to be true. Instead, he derived Kepler's third law from his two premises. This is what it means to say that an inverse square law is logically consistent with Kepler's laws. Newton found that if he took as his second premise a simple inverse law, that is, force is proportional to 1 over r, he could not derive Kepler's third law. Similarly, if he took as his second premise an inverse cube law, he likewise could not derive Kepler's third law. So, let's try to replicate how Newton would have proceeded in greater detail. We begin by drawing a diagram of a planet in a circular orbit of radius r. Then we draw a velocity vector indicating the initial velocity of the planet in this thought experiment and label that vector v sub I. I would point out here that the velocity vector of a planet is always tangent to its orbital path, for it would be logically impossible for the velocity to be directed elsewhere. By the way, we are going to identify this diagram as a diagram in position space to distinguish it from a diagram in vector space, which we will introduce in a moment. In the absence of gravity, the planet would move directly to the right in this diagram. But in this thought experiment, we assume a circular orbit, so there must be a force attracting the planet toward the sun. Furthermore, that force needs to be maintained continuously, or else the planet will fly off on a tangent. All this is generally consistent with the law of inertia, but more specifically, it reflects Descartes' second law of nature. That is, every motion is in itself rectilinear, and therefore things which are moved circularly always tend to recede from the center. So, essentially, gravity needs to cause the planet to accelerate towards the sun by just the right amount, so that the planet neither recedes from the center nor spirals inward towards the sun. Now we are ready to actually begin our thought experiment. Let's let an amount of time elapse and call that amount delta t. After delta t has elapsed, the planet has moved to a new position on its circular path. I have drawn in another radius in the appropriate spot and labeled the angle between the two radii as theta. For the purposes of the discussion that follows, we must think of theta as measured in radians. The planet has a new velocity vector, and we label it v sub f because this is the final velocity at the end of the elapsed time. Question: is the vector v sub I equal to the vector v sub f? No, because their directions are different. However, let's just consider their magnitudes. When I refer to a velocity vector without an arrow on top, I am referring only to its magnitude. Here's where we use Kepler's second law as a premise. Because the radius is constant, the area swept out in a given amount of time can only be a constant if the magnitude of the velocity is always the same. So, the magnitudes of v sub I and v sub f are equal. So, for convenience, let's refer to that magnitude simply as v without any subscript. S is the arc length of a segment of a circle, and it represents the distance traveled along the planet's circular orbit during delta t. S equals v times delta t. In accordance with the principles of geometry, it is also the case that S equals r times theta. I have drawn the green vector here and labeled it d to indicate not the distance traveled, but rather to indicate the displacement of the planet. That is, the sum total change in its position. We can see that d is approximately equal to s. Now the choice of delta t is arbitrary. Newton realized that he could make delta t as small as he wanted, without affecting the logic of his derivation. You can easily imagine that if we make delta t smaller and smaller, d and s become smaller and smaller, and the difference between them becomes smaller and smaller. There is a formal way of expressing that statement mathematically. As delta t approaches 0, d approaches 0, and s approaches 0. However, the real question, mathematically speaking, is what happens to the ratio of d to s. As d goes to 0, you might think that the ratio goes to 0. However, as s goes to 0, you might argue that the ratio goes to infinity. Which is it? 0, infinity, or something in between? Spoiler alert, Newton will show that the ratio goes to 1. In other words, d becomes equal to s. Newton would have called this question the problem of vanishing quantities. Another term he would use for vanishing quantities is infinitesimals, quantities that are unimaginably small, smaller than any real number. Developing a strategy for dealing with infinitesimals and vanishing quantities is the essential first step in inventing calculus, which is exactly what Newton was doing around the same time. In modern terminology, this strategy is known as the theory of limits. This is the perfect time to talk about another ratio of vanishing quantities that we need to deal with. This investigation will also lead us to conclude, as Newton did, that in fact d equals s as delta t approaches 0. We begin by remembering that s equals r times theta. The purpose of this next move may not be immediately obvious. If we think of the two radii and d as forming a triangle, I have drawn here an altitude of the triangle from one radius and perpendicular to it to the opposite vertex. Here's where we draw upon some basic trigonometry. A divided by r is the definition of the sine of theta. We can state this alternatively as A equals r sine theta. Now, obviously, as delta t goes to 0, theta goes to 0 and A goes to 0. And if A goes to 0, then sine theta must go to 0. The question is, what is the ratio of theta to sine theta as delta t goes to 0? The answer is this. In the limit as theta goes to 0, the ratio of theta to sine theta equals 1, or in other words, theta equals sine theta. There exists an elegant proof of this relationship that is based on geometry and trigonometry. Once again, though, in general, it raises the issue of the ratio of vanishing quantities. Newton and his contemporaries wrestled with the problem, and a fully satisfactory theory of limits was not developed until after Newton's time. There were occasions when such a ratio could not be determined with certainty, and Newton had to rely on his mathematical intuition. His mathematical intuition was usually correct. As James Glick wrote in his biography of Newton, he drew lines and triangles that looked finite but were meant to be on the point of vanishing. Then he quotes Newton directly. Newton wrote, "It may be objected that there is no such thing as an ultimate proportion of vanishing quantities, inasmuch as before vanishing the proportion is not ultimate, and after vanishing it does not exist at all. But the answer is easy. The ultimate ratio of vanishing quantities is to be understood not as the ratio of quantities before they vanish or after they have vanished, but the ratio with which they vanish." So let's substitute theta for sine theta as shown and summarize. In the limit as delta t goes to 0, A equals r theta, and therefore S equals A. What about D? Well, D is sandwiched in between A and S. It can never be more than S nor less than A. So we conclude S, A, and D are all equal in the limit. In modern-day formal terms, this proof is an application of the squeeze theorem. At this point, like Newton, we are drawing lines and triangles that look finite, but are meant to be on the point of vanishing. So, going forward, we will take D as equal to S, even though our diagrams will contain finite figures. So let's go back and consider the triangle whose three sides are R, R, and D. We no longer need to emphasize that D is a vector. We are only concerned with its magnitude or length. So I have removed the arrow above the D. This is an isosceles triangle. It has two sides of equal length, R, and these sides are known as the legs. The side labeled D is known as the base of this isosceles triangle. The two angles at the base of an isosceles triangle are equal. Let's label them phi. As in all triangles, these three angles must add up to 180 degrees. So we write theta plus 2 phi equals 180. Rearranging, we get phi equals the quantity 180 degrees minus theta, all divided by 2. We'll come back to this later. For now, let's add the velocity vectors back in. And now we are going to move them into vector space. So here's our vector space, and as I move vectors into it, I'm going to increase their magnitude by 50%. just so that we can see what's going on a little easier. The point is that you can change the scale in vector space as long as you treat each vector the same way. So here's v sub I scaled up by 50%. But when we move vectors into vector space, we must always maintain their same orientation as in position space. Now we place v sub f in vector space, and I have put the tails of the two vectors together at the same point because I want to make v sub f the resultant of v sub I plus one other vector. You can immediately see where this new vector needs to go in accordance with the rules of vector addition. So let's draw it in. And label it delta v. Now the angle between v sub I and v sub f is theta. That might be apparent to you already, but let's prove it. First, let's clean up the diagram and create some workspace. Notice that I have labeled the radii r1 and r2 so we can distinguish between them. Remember that the velocity vectors are always tangent to the circle. A tangent to a circle always forms a right angle with a radius drawn to the point of tangency. Here I have indicated the two right angles formed by v sub I with r1 and by v sub f with r2. Now, for our proof, we need a 0-degree reference direction. And here it is. Now I'm introducing a notation, circled in green, to refer to, in this case, the angle of r1 relative to the reference direction. Angle r1 equals 90 degrees. It was originally drawn that way intentionally. What about angle r2? Its actual value is not important, so let's call it A. Theta is the difference between angle r1 and angle r2, so we write theta equals angle r1 minus angle r2. Therefore, theta equals 90 degrees minus A, or A equals 90 degrees minus theta. Let's put a box around that. We'll need it in a moment. Okay, what about the angle of the initial velocity vector v sub I? V sub I is rotated 90 degrees clockwise relative to r sub 1. So we can say that angle v sub I equals angle r1 minus 90 degrees. In this case, the negative 90 degrees represents the clockwise rotation relative to r1. Substituting for angle r1, you can see that angle v sub I equals 90 degrees minus 90 degrees, or 0. Let's put a box around that result. Similarly, angle v sub f equals angle r2 minus 90 degrees, or A minus 90 degrees. Substituting for A, we get angle v sub f equals 90 degrees minus theta minus 90 degrees, or simply negative theta. Finally, we are in a position to find the difference between angle v sub I and v sub f. Referring to the values in the purple boxes, we see that angle v sub I minus angle v sub f equals 0 degrees minus negative theta, or simply theta. QED. Now let's go back to where we left off. I want to draw attention to the fact that the triangle in vector space is an isosceles triangle, so I am going to transform the velocity vectors to line segments and label them with their magnitudes. The angles at the base must be the quantity 180 minus theta, all divided by 2, or phi. So now it's clear that the triangle in position space and the triangle in vector space are similar isosceles triangles. That means that the ratio between any two sides of one triangle equals the ratio between the two corresponding sides of the other triangle. So d divided by r equals delta v divided by v. Now substituting for d, we get the quantity v times delta t divided by r equals delta v divided by v. Rearranging, we find that v squared over r equals delta v divided by delta t. Now, delta v divided by delta t, as we learned from our study of Galileo's work, is acceleration, or a sub c. The subscript c indicates that this acceleration is centripetal, that is, towards the center of the circle. Recall that earlier we found that a sub g, the acceleration due to gravity, is equal to capital G times capital M, all divided by r squared. Now let's set a sub c equal to a sub g. This is the condition for a circular orbit. That is, it creates the situation where the acceleration due to gravity matches the centripetal acceleration necessary to produce a circular orbit. Therefore, v squared divided by r equals gm divided by r squared. With this finding in hand, we're almost done. I've created some clean workspace so we can finish up. First, let's solve this expression for v. V equals the square root of g times m divided by r. Let's draw a red box around this expression for v and save it for later. We have derived this formula from Newton's law of gravitation and Kepler's second law applied to a circular orbit. Let's derive one other formula from Kepler's second law. We return now to one of Newton's premises, Kepler's second law. Kepler's second law is concerned with the area, delta A, shown here, swept out by the planet during a certain period of time, delta t. Delta A is indicated by the sector of the circle here shaded in purple. One way of stating Kepler's second law is to say that delta A divided by delta t is a constant. I've represented this constant here as k, and we want to find another expression for k. Newton knew, as did the ancient Greeks, that the area of a sector of a circle, in this case delta A, equals 1/2 times theta times r squared. For reasons that will become immediately clear, I'm going to rewrite the right side of this equation as 1/2 times r theta. As I earlier stated, s equals r times theta, so we can substitute s for r theta in our equation for delta A. Furthermore, we know that s equals v times delta t, so we can substitute this expression for s. Now we divide both sides by delta t, and we find delta A divided by delta t equals 1/2 times r times v. And the right-hand side of this equation represents the alternative formulation for k that we have been looking for. Let's put a red box around this formula and transfer it to some clean workspace along with the other formula that we found just moments ago. So here we go. Let t equal the period of the orbit. In other words, the time elapsed for one complete revolution around the Sun. It follows logically that t times the area swept out per unit time equals the area of the entire circle. And the area of a circle equals pi times r squared. Here I've substituted our expression for delta A divided by delta t. And here I've substituted our expression for v. Now we square both sides of the equation. We can simplify the left-hand side just a bit by dividing r squared by r. Now we can multiply both sides by 4 and divide both sides by g, m, and r. Now the quantity 4 times pi squared divided by g times m is a constant. And so it is correct to say that t squared is proportional to r cubed, which is Kepler's third law. So Newton has succeeded in proving Kepler's third law, starting with Kepler's second law and his inverse square law for the universal law of gravitation. Of course, as we have emphasized, this proof is valid only for circular orbits. Newton will continue working on this problem off and on over the next 16 years, until he derives all 3 of Kepler's laws from first principles, namely his 3 laws of motion and his universal law of gravitation. As you can imagine, this undertaking will be immensely more challenging when considering non-circular orbits. Newton's own proof in the Principia will be extremely difficult to understand, not only for other scholars of the time, but also for physicists who came later. Although Newton invented calculus, and calculus represents the conventional approach to the problem today, Newton relied instead almost exclusively on arguments based on highly advanced geometry, including some obscure principles going all the way back to the ancient Greeks. Even the great Nobel Prize-winning physicist Richard Feynman admitted that he couldn't understand all of it. As a Cambridge student at the time allegedly commented as Newton walked by, "There goes the man that writ a book that neither he nor anybody else understands." The approach using calculus is understandable only after one has learned advanced techniques in solving complex differential equations. There is a third approach for those of us with only a background in high school level math, but one must be patient and persistent. If you are interested, you can see how it is done in my video series, Solving the Kepler Problem Using Only Newton's Laws, High School Level Math, and an Intuitive Approach to Infinitesimals, which you can find also on this same channel, Voltaire's Garden.